Hello, I'm Dave Brown for Teletrain, and today we continue our study of Parker Hannafin's text on industrial pneumatic technology with Chapter 4. It covers the control of pneumatic energy. First off, energy that is transmitted through a pneumatic system must be directed and under complete control at all times. If it isn't, useful work may not be done, and machinery or machine operators could be harmed. One of the biggest advantages of using a pneumatic system to do work is that the pneumatic energy can be controlled relatively easily by using devices which are called valves. Here are some typical valves you'll find in a pneumatic system. This one is a pressure regulator. It's used to control or regulate the air pressure in a certain part of a pneumatic circuit. This one is a directional control valve. Its most common use is to control the direction of flow of air to and from a pneumatic cylinder or motor and thus change actuator direction. Finally, this one is a needle valve. Needle valves are used to regulate the flow of air within a pneumatic system. Well, although these valves perform different functions, mechanically, they have the same basic parts. Here's one cut open so you can see what it looks like inside. The outside housing here is called the valve body. Then there is this internal moving part here that controls the flow of air by connecting or disconnecting these passages within the valve body. The valves you've just seen are used in pneumatic systems for three main purposes: to control the air pressure within the system, to direct the flow of air to the various circuit components, or to regulate the flow of air within the system. Now let's examine why pressure control valves are necessary and how they work. Pressure in a pneumatic system must be controlled at the 2 points you see here, at the output of the compressor and at the point of use. Why at these 2 points? Well, control of pressure is required at the compressor as a safety for the system. If the pressure was allowed to rise uncontrolled, excessive pressure would be developed and the air receiver tank might rupture. Control of pressure at the point of use, such as at this actuator, is necessary for safety also. But more important, it assures that the actuator receives just the right pressure to operate without wasting air. As we explained in Chapter 3, the energy delivered by a compressor is not used immediately, but is stored as potential energy in an air receiver tank. The system receives compressed air from this tank in order to perform work. And of course, the pressurized air must be replaced. That's the job of the compressor, like the one shown here. You'll find that in most applications, a compressor is designed into a system so that it operates on an intermittent basis. When the compressor is running, it delivers compressed air to the tank until a specified pressure is reached. Then it automatically shuts down. On smaller horsepower compressors, the device we use to sense tank pressure and to control actuation and deactuation of the compressor is a pressure switch, like this one. Here is the inlet port, connected to the tank, and here is where the electrical contacts are housed. They are used to turn the electric motor on or off. We can explain its operation by using this drawing. It shows all the main parts. This is the switch body, and here is the inlet opening we saw earlier. Inside the switch body, there is a piston held in place by a spring. A rod on the piston here that is connected to and operates the electrical contacts. When the system or tank pressure is low, the spring forces the piston down, as you see here. In this position, a contact is made, and this causes an electrical signal to turn on the compressor. As air pressure in the system increases, it enters the switch through the inlet. The air pressure pushes the piston up, thus compressing the spring. When the air has reached a high enough pressure, the piston has moved so the electrical contacts are opened, and the electric motor and the compressor are shut down. The use of pressure switches like the one we just described is common for most small compressor applications, say in the 1 to 10 horsepower range. For larger units, however, it isn't practical to start and stop. We use techniques that unload the compressor, that is, prevent it from compressing air during the compression stroke while leaving the compressor and motor running. However, more on this in Chapter 5. Even though switches are very dependable and do a good job of controlling compressor cycling, we need some means of sensing and relieving pressure just in case the control system fails to function properly. One of these devices should be installed in every system. It's called a safety relief valve, and in most applications, its use is actually required by law. Let's identify the main parts and then examine how it works. This is the valve body, and you can see there are two openings, the inlet port here and the exhaust port here. Inside, there is a movable part called a poppet. The poppet is held in place against the seat by a spring. Also, you can see that the poppet has a plunger attached that is connected to a manual test lever. The inlet port is connected to the part of the system we want to protect, and under normal or safe operating conditions, the inlet is sealed by the poppet. Suppose that we have a pressure switch controlling a compressor and the pressure switch fails with the compressor running. What would happen? Well, if the compressor continues to run, the system or tank pressure will build up. When the pressure of the air against the poppet is greater than the spring force, the spring will be compressed and the poppet will move off its seat as you see here. When that happens, there's a path for air to flow from the inlet to the exhaust port, thus relieving the pressure. In addition to the noise of the escaping air, many safety relief valves are equipped with whistles or horns to alert the operator that there is a problem in the system. As you might suspect, in most pneumatic systems, safety valves which monitor compressor output are not intended to be operated frequently. But for that one time, they have to work. It's important to know they will. That's why safety relief valves are equipped with a manual test lever. It allows an operator regularly to activate the valve manually to make sure it's not clogged or that the poppet has not become jammed in the valve body. Periodic checks of safety relief valves to make sure they move freely is an essential part of a good maintenance program. So be sure to follow the schedule specified by your supervisor and/or preventative maintenance schedules. Well, both pressure switches and safety relief valves are used primarily to control the pressure at the air receiver tank. But it's important also that we be able to control or regulate the air pressure that goes to the other parts of the circuit. Here is the device that we use. It's called a pressure regulator, and most regulators look pretty much the same, no matter who makes them. Here is the inlet port, and this is the outlet port. You'll hear the inlet referred to as the primary side and the output as the secondary side. This is the adjustment screw. It is set manually by turning it to obtain the desired output pressure. It will be easier to explain how a pressure regulator works if we use a drawing that shows the internal parts and how they move. This is the valve body, and these are the inlet and outlet ports we mentioned earlier. You can see that air flows through this passage, past this moving part called a poppet. The poppet controls the size of the opening between the primary and secondary passages and is attached to this piston. The piston is held in the down position by a spring, and spring pressure can be adjusted using this adjustment screw. As we will explain, this passage, called the pilot passage, is very important to regulator operation. Finally, this chamber, which houses the spring and piston, is vented to the atmosphere through this small opening here. I should mention here that there are also non-vented types which work on the same basic principle. Okay, let's see how the pressure regulators work. The pressure regulator is a normally open valve, which means that the poppet is positioned, as you see, so that air can flow freely from the tank through this passage and into the circuit. When pressure rises, it is transmitted through the internal pilot passage and pushes against the surface of the piston. Because the piston has a large surface area exposed to the secondary pressure, it is very responsive to pressure changes in the output side of the regulator. When the controlled pressure reaches the preset value, the piston moves upward, and the poppet begins to close off the primary to the secondary passage. If the secondary pressure rises enough, the poppet closes off the passage completely, so that pressure cannot continue to build downstream in the circuit. Here is a pneumatic circuit which shows the placement of the system components we've covered so far. You can see the relief valve and pressure switch are located at the output of the compressor on the receiver tank. The pressure regulator is placed in the system downstream near to the point of use. A pressure regulator ensures that energy in a system will not be wasted. For example, if an air receiver charged to 100 psia were allowed to apply its full pressure to an actuator that required only 60 psia, energy would be wasted. A device used to convert air pressure to mechanical force is a double-acting cylinder, like the one you see in operation here. By directing the flow of air into the proper cylinder port, the actuator can be made to change direction. This illustration shows the main actuator parts. The double-acting cylinder has a port at each end. We've labeled them Port A and Port B. It is called a double-acting cylinder because this piston is free to move in either direction. If pressurized air is directed into Port B, here, the piston will move to the right, and the rod attached to the piston will extend. On the other hand, if we direct air into Port A, the piston will move to the left, and the actuator rod will retract. So to make the double-acting cylinder work, we need some way that we can change the direction of air flow to and from the cylinder. And we do this by using what is called a directional control valve. Here is what a typical directional control valve looks like. There are openings or ports in the valve body. These allow connection to the ports of an actuator, like a double-acting cylinder, and to the air supply and exhaust. Now right here, I'd better mention that different manufacturers use different letters and numbers to identify these ports. You should check their literature before making an installation. Inside the valve is this moving part called a spool. It consists of a shaft with lands which connect and disconnect internal passages in the valve body. Here is how it would look in an actual circuit. When the spool is pushed all the way to the right, air is free to flow from the inlet line, P, through the valve to Port A. Port B is connected to the exhaust side of the valve. The pressure of the A side will move the cylinder piston to the right, and the rod will retract. If we push the spool all the way to the left, the passages in the valve body are connected, so Port B is now connected to the inlet line, and Port A is connected to the exhaust. With the B port pressurized, the rod will extend. So the combination of the directional control valve with double-acting cylinder allows us to extend or retract the actuator rod. But if we want to control the rate at which work is performed, then we must control the speed at which the actuator moves. In a pneumatic system, the speed of the actuator depends upon how quickly the actuator can be filled and exhausted of air. The greater the cubic feet per minute that flows into the inlet and out of the exhaust port, the more rapidly the piston will move. But before we examine flow, we should understand a couple of important facts about pneumatic circuit operation. Remember the regulator we talked about earlier? Its job was to portion out to a certain leg in the circuit just the pressure required to equal the load resistance plus a little more. This additional pressure is used to develop airflow. Even so, pressure regulators are not used to vary actuator speed. When we require some means of restricting airflow to or from the actuator, we do this with a device called a flow control valve. In most cases, this is a needle valve or needle valve with a bypass check, like the one shown here. And here is a very important point to remember. The valve will maintain constant airflow only if the resistance the actuator encounters, and that's the total load consisting of friction and the load itself, are constant. And the pressure both at the inlet and the outlet of the cylinder do not vary during the entire work cycle. So in actual fact, the needle valve does not control flow. It really only affects flow. And if we had the regulator and the flow control valve set up in a circuit for a certain speed, and then we increased the load, the speed would decrease. And if the load increased enough, it could cause the actuator to stop. Now let's look at that needle valve again. It consists of this valve body with both inlet and outlet ports. Adjustments are made with this adjustment knob. Here's a cross-sectional view. The inlet and outlet ports are connected by this internal passage here that has been formed into the valve body. You can see that the adjustment screw is threaded. So by turning the knob here, you can raise or lower this tapered tip against the valve seat. The smaller the opening around the tip, the more restriction to airflow there will be, and the lower the flow rate. If we place this valve in the exhaust side of a double-acting cylinder, airflow leaving the cylinder will be reduced, and a back pressure will be developed against the surface of the piston. This back pressure serves to cancel out some of the force being applied to the other side of the piston. Since there will be less force available to create motion, actuator speed will be reduced. Because it's so important, we should stress this point one more time. It is possible to control the speed of an actuator by restricting flow using a needle valve only if the total load on the cylinder remains constant. So if load resistance changes any time during the cycle, actuator speed will vary, even though the valve has been preset. Here is a basic pneumatic system that uses all of the components we've examined so far. It will perform work because the energy in the form of compressed air can be controlled. Let's follow the flow through the circuit. The compressor is being driven by a prime mover. It could be an electric motor, a gasoline engine, and so on. The compressed air flows to the air receiver tank. Note that our system contains both a pressure switch, which causes the prime mover to turn on and off at a pressure setting, and the safety valve that would relieve system pressure should the pressure switch fail to work. This pressure regulator on the downstream side of the air tank reduces tank pressure to the value that will make this portion of the circuit operate most efficiently. The output from the regulator is fed into this directional control valve. It directs the flow of air to the proper port on this double-acting cylinder. And finally, to obtain desired actuator speed, this circuit uses a flow control valve located in the exhaust side of the cylinder. Up until now, all of the system components have been shown pictorially. But for working drawings, where circuits can become much more complex, this technique just isn't practical. So instead, when system drawings are made, symbols are used to represent the particular circuit element. To be able to read and understand these kinds of drawings, you'll want to be familiar with the symbols and what they mean. Now, although there is normally no color used on a standard circuit diagram, we've added a color to each symbol to make it easier to recognize. We'll be using these symbols throughout the remainder of the course. Here are the ones we've covered so far. This is the symbol for a compressor, which we've colored orange. Here is the way we represent a pressure switch. Note the dots, which represent the electrical contacts and the way the spring is shown. This is the symbol used to represent the air receiver. It looks a lot like the pictorial drawing. The symbol for a directional control valve is a bit more complex, but you can see how the lines with arrows are used to indicate how passages are connected and the direction of air flow through the valve. We've colored it blue, as we have all other valve symbols. A double-acting cylinder is represented like this. You can see both ports and the piston. A cylinder will always be colored green in these programs. The last component we examined was the flow control valve, and here is how it is represented. Finally, here are the other graphic symbols that are used on drawings for fluid power. They are shown on page 32 of your text, and you may want to refer to them until you commit them to memory. Now let's explain color coding to represent air in various parts of a system. Red indicates supply pressure. Orange can mean either reduced pressure or pilot pressure. Yellow indicates metered flow. And blue stands for exhaust. When the air is colored violet, it will indicate an area of intensified pressure. These colors are the ones accepted as the international standard. Okay, before we finish, let's see how that basic pneumatic system looks when we substitute the symbols for the pictorial illustrations. Here it is. Can you identify the compressor? It's right here. Or the air receiver tank? This is it. And how about the double-acting cylinder with flow control valve? If you said this is it, you're right on target. Well, you'll find the more you use these symbols, the easier they will be to remember. Now turn to page 34 of your text and do the exercises that you'll find there. This ends Chapter 4 of Industrial Pneumatic Technology. I'm Dave Brown for Teletrain.